Hey folks, how's it going? Good? Good? Good, good, good. How'd that last homework assignment go for you? Feeling good? Let me just kind of recap a little bit. We have started a new unit on propositional logic. It is a slightly different approach than categorical logic. Both of them are all about deduction. So we're concerned with the form of these arguments more than their content in order to establish whether or not they're valid. Their content will determine whether or not the premises are actually true or not, but we can figure out whether they're valid without looking at the content at all. We can symbolically represent the content and just look at the form. At our last meeting, we discussed these four logical operators. And we identified that in propositional logic, the letters that I'm using to kind of symbolize the different parts that are being related are complete, freestanding propositions. They are independent propositions. They have a truth value all on their own. In categorical logic, our letters were just categories. They weren't propositions. Our categories were things like cats or dogs or mammals. And cats isn't true or false all by itself. All cats are mammals. That's the sort of thing that's true or false. But cats all by itself, not a proposition. On the other hand, if I'll look at something like this, where Bob ran and Alice walked, Bob ran is a proposition, Alice walked is a proposition. Bob ran and Alice walked is a complex proposition made up of two different propositions that are then linked by this logical operator. That logical operator is the conjunction operator, sometimes called the and operator, and we've been representing it with an ampersand. We also looked at the disjunction, or the or operator, and that's represented with this wedge. We looked at negation, it's represented with the tilde, and the conditional operator, which is represented with this arrow. That's the if-then operator. And I'll also point this out. There's a sort of syntax to the way that all of these logical operators are used. And or have to have two independent statements that they're kind of linking, that they're operating on, right? There's got to be something before the and something after the and. And the and operates on what is immediately to its left and right, saying that like both of them are true. It's going to have, the way that we talked about this is, every conjunction has two conjuncts. And the syntax of how to use these operators is one conjunct is on one side of the ampersand, the other conjunct is on the other side of the ampersand. Same thing going on with my or operator, or the wedge symbol. A disjunction always has two disjuncts. One of them is going to be on one side of the wedge. One of them is going to be on the other side of the wedge. The tilde, or the negation operator, the not operator, is a little bit different. It doesn't have two independent statements that it's operating on. It operates on whatever is immediately to its right. And the if-then, like and or, has two parts. One of the things that's different and interesting about the if-then or the conditional operator is that the order matters. For and or, the order doesn't really matter. I could say P and Q, or I could say Q and P. It means the same thing. Does that sound about right? I ate an apple and a pear. I ate a pear and an apple. Both of those are only going to be true if I ate both a pear and an apple, right? And false in every other condition. Same with or. I had an apple or a pear. I had a pear or an apple. Means exactly the same thing. Not so with the conditional. We have different names for each of the two parts. The thing that comes before the if-then, the if part of the if-then, is called the antecedent. The part that comes after the if-then, the then part, is the consequent. Yeah, we have an antecedent and a consequent. But the syntax is such that there has to be something immediately to the left of the arrow, something immediately to the right of the arrow. That's what the arrow does. It's saying if the antecedent happens, then the consequent will happen. Yes, Amin. Could I add a third variable? Like what? What kind of statement do you have in mind? Something like P arrow QS? Yeah, something like R. Or P arrow QR? Yeah. So what would that mean? If P then QR? Yeah, it would be weird. Let's imagine P is Tim studies. Q is he aces his logic exam. R is he eats a sandwich. If Tim studies, then he aces his logic exam, Tim eats a sandwich. That's a little weird, right? Maybe I want to say and Tim eats a sandwich. If Tim studies, then he aces his logic exam and eats a sandwich. And now I have this question where, like now, I'm going to do another conjunction, right? It's going to be P arrow Q ampersand R, where R is he eats a sandwich. And now I have this question of like, how am I going to parse this? Is it if P then Q and R, or is it if P then Q and R? Yeah, right? There's a little ambiguity. And today we're going to start, in fact, at our last meeting, we already started looking at scenarios where I have to kind of demystify that ambiguity, and I do it with parentheses. Parentheses are going to help me figure out whether I'm saying if P then Q and R, or if P then Q and R. If I wanted to do the latter one, if I wanted to say if P then Q and R, I do if P then, and then parentheses, Q and R. If I don't have those parentheses, then it's more like the first version. If P then Q and R. And if I wanted to like settle that and make sure that nobody misunderstood what I was saying, I'd maybe put if P then Q in parentheses, and then do the ampersand and then R. Yep. Good question. Yep. How are we doing so far? Also at our last meeting, we talked about defining each of these operators in terms of a truth table. So we've already introduced this idea of a truth table. And we've introduced this idea that like there's a rule for each of these operators that's going to determine when using that operator is going to yield a true or a false complex statement. So I have P, I have not P. Not P is going to be true when P is false, and it's going to be false when P is true. The negation operator just flips the truth value of whatever it's operating on. The and operator, conjunction, the rule for this was what? It's true. When is it true? It's true only when both conjuncts, always and only when both conjuncts are true. In every other case, it's false. If only one of the conjuncts is true, when I say apples and oranges, I mean both, right? So if it's just apples but not oranges, then apples and oranges is not gonna, apples and oranges isn't a statement. I ate apples and I ate oranges. That's only gonna be true if I did, in fact, eat both. If either one of those conjuncts is false, the whole conjunction falls apart. Disjunction, what's the rule here? Well, at least one of them has to be true. Yeah, not exactly one, but at least one of them has to be true. It's exactly one if it's an exclusive or, but we've been assuming that this is an inclusive or. We could make this more complicated by considering two different versions of or, but honestly, it's complicated enough already. Let's not make things harder on ourselves than we need to. And the rule here, yeah, is at least one of the two disjuncts has to be true. Another way of saying this is it's always true except when both disjuncts are false. And then last but not least, for my conditional statement, there's only one scenario under which the conditional is false, and that's when the antecedent is true and the consequent is false. My experience is that this is the hardest one for folks to get the hang of. One thing to try to keep in mind is that for a conditional statement, whenever the antecedent is false, the whole conditional statement is going to be true. Because it will always be consistent with a conditional statement to entertain some scenario where the antecedent is false. That conditional statement only talks about what happens when the antecedent is true. So if P then Q, if it rains, then I'll bring my umbrella. I'm only talking about what happens if it rains. If it doesn't rain, anything goes. I haven't specified what happens in that case. So any kind of scenario where my antecedent is false is still going to be consistent. Whoa, where'd I go there? Still going to be consistent with an if-then statement. Somebody alerted me, by the way, to a mistake on this slide at our last meeting. I had something a little wonky here in the, I think it said before, I think it said something like, it fits provided that I sits, means the same thing as if it fits, then I sits. It should be the other way around. I corrected that by now. Hope that wasn't really too confusing for anybody. But the point here is there's a wide variety of natural language formulations that can be represented in this same symbolic form. At this point, I'm going to expect that everybody has these four rules for these four operators more or less in their pockets. If you're feeling a little wonky on this, you might want to have that cheat sheet from our last class meeting that had the truth tables for each of those operators. You might want to have that out for what we're doing today. You might want to have it out anyway, just because we're going to be building on this. We're going to be seeing what we can do next. On the worksheet at our last meeting, we did a whole bunch of translations from natural language, and then we had this business where I told you that P, Q, and R are true, and X, Y, and Z are always false, and you had to figure out what the whole statement was. How'd you feel about that? That was a little tricky? Some folks like yeah, some folks no. We're going to be digging a little deeper into this today, looking at how we handle this, and we're going to be looking at it in scenarios where I haven't been told that P, Q, and R are true and X, Y, and Z are false. I'm going to be looking at scenarios where I have no idea whether my simple component propositions are true or false, and so I need to consider every conceivable scenario. I need to consider like all of the possible combinations of truth values for all of my simple propositions. For example, and a truth table, we've already seen truth tables. We've seen them in how we're defining our operators. A truth table is just a representation of every possible combination of truth values for all of the simple component propositions in a big complex proposition. So let's start over here. This is a complex proposition. It's not very complex. It's one of the simpler versions of a complex proposition that we could have. A is a proposition, B is a proposition, and then I combine them into one grand complex proposition with the AND operator. So I'm saying A and B. A and B could be anything here, right? A could be like Adam eats a sandwich. B could be he takes a disco nap. So this would be Adam eats a sandwich and he takes a disco nap. Cool? When A is true and B is true, A and B is true. When A is true and B is false, A and B is false. When A is false and B is true, A and B is false. When they're both false, A and B is false. Do we get how this is like all of the possible combinations of truth values for A and B? A could be true or it could be false. But I need to consider A as true twice because there's a version of this where A is true and B is true, and then there's another version of it where A is true and B is false. Same thing goes down here. A could be false, and I need to consider two different versions of false A. There's one where A is false and B is true, and then there's another one where A is false and B is also false. If there are two possible truth values for A and B, and I can combine them in any number of ways that I try to, I'm going to end up with 4 lines on this truth table. And what's revealed here is that, all right, so these are the truth values of the whole statement. Whereas in this column, I have just the truth value for A, in this column, just the truth value for B. And I'll note that only under one of those circumstances is A and B true. So I don't necessarily know whether A is true or false. I don't necessarily know whether B is true or false, but I do know this. I know that my statement A and B is only ever true when both of the conjuncts are true. I've identified what it is that's going to make this statement true. This is, you might be looking at this and you're saying like, old news, Rosenfeld, show me something new that I don't know. Okay, let's use this exact same method to handle this proposition. This proposition is complex. This proposition is very complex. It has multiple operators in it. What I'm saying here is, and here's how I would kind of read this out loud. We'll get a little bit of practice with this today. I would read this as if A or B, then not B. Notice I have parentheses here and here to kind of group all this together. That's the antecedent for my conditional statement. And then the consequent for my conditional statement is this whole big ball of wax here. It's not B. Does that make sense? Now I have A in this. A is one of my simple propositions, and B is one of my simple propositions. Do I have any other simple propositions besides A and B? Nope. Nothing but A's, B's, and logical operators in here. I don't have a C or a D or a Q or an R or anything like that. Just A and B. Well, notice that B occurs twice, but it's not a whole brand new proposition. What we're going to be thinking about here is like, what are the possible combinations of truth values for A and B? They could both be true. A could be true while B is false. A could be false while B is true. Or they could both be false. And that's everything. Those are the only possible combinations. Whenever A is true, I'm going to, over here, label A as true. Whenever B is true, I'm going to label B as true. Whenever A is false, I'll label A as false. Whenever B is false, I'll label B as false. I'm basically just repeating what I've said over here for every occurrence of A and B. Does that step make sense to you guys? You see what's going on? I'm just plugging in the values for each row. This row is a world. It's a possible world where A and B are both true. In another possible world, only A is true, but B is false. In yet a third possible world, A is false and B is true. And in a fourth possible world, they're both false. And those are all of the possible worlds involving like truth and falsity for A and B. I plug them in to my big complex statement, and now I have to start trying to figure out the component parts of this complex statement before I can figure out like the truth value of the whole thing. What do I mean by that? Well, I mean that there are many different places where I could be attacking this proposition. Like, for example, can I figure out whether if A or B, then not B, can I figure out if that's true or false yet, if A is true and B is true? I see some people going, yeah, some people going, no. What's going to make this true? It's a conditional statement, right? So it's going to be true whenever maybe we'll look at it when it's false. It's false when the antecedent is true and the consequent is false. Do I know if the antecedent is true?
Yes.
I do. Well, not quite yet. I know that A is true and B is true, and I know that the antecedent is A or B. I can figure it out real quick. If A is true and B is true, then A or B is true. If B is true, then not B is false. Now I can do this conditional statement, right? Because I know what A or B is. On this line, it's true. And I know what not B is. I know what the consequent of the conditional is. On this line, it's false. B was true, so not B is false. If I have a conditional statement that has a true antecedent and a false consequent, then the conditional statement is false. That's the only time. So for this row, in the possible world where A and B are both true, this whole complex proposition is false. Yes, Kenneth?
So essentially what the goal is to get those complex propositions to their simplest form.
Yeah, so I'll identify like the simplest components of this. And the simplest components are my component simple propositions, right? All of my letters in this business. And then I want to look at like the groups of complex propositions, and I want to figure those out first before I do the whole thing. There's going to be some sort of like order. There is an order of operations to this. There's a syntax, just like there is in mathematics. The syntax usually works as do whatever's inside the parentheses before you do outside of parentheses. You've seen that before, right? And go left to right is another principle that you want to apply. And then the other thing, too, is remember the syntax for each of these logical operators. An OR operator, or a wedge, always operates on immediately what's to its left and right. That's what it's ORing together, is whatever is to one side and whatever is to the other side. An if-then operator, the conditional operator, is going to say whatever is immediately to its left is the antecedent, whatever is immediately to its right is the consequent. Yes?
Could you clarify the goal
Of what we're doing here? Yes. The goal of what we're doing here is we want to find out under what conditions is that whole big statement true. Under what conditions is it true? Under what conditions is it false?
which is different from its validity?
Which is different than its validity because a statement does not have validity. Statements can be true or false. What can be valid? Arguments can be valid. Arguments have many statements in them. A couple of premises and then a conclusion. This method, not today, but soon, we'll be looking at using this method for not just one statement, but many different statements, where I'm saying, like, this one's a premise, this one's a premise, this one's a premise, this one's a conclusion. And then I'm going to use this truth table method to try to figure out if the argument's valid by trying to see if there's a scenario where all of the premises are true and the conclusion is false. But we're not there yet. First, like, we'll walk before we run. Right now, what we're wondering about is, like, under what conditions is a statement like this true? And a possible immediate goal of this is somebody gives you a statement like this. Somebody says, if A or B, then not B. Well, they like flesh it out with some content, and you're sitting there wondering, like, is that true? Well, you can kind of you can streamline this question of whether or not that statement's true by first determining under what conditions would it be true. In what possible worlds is it true, and in what possible worlds is it going to be false? So for this line, where A and B are both true, the whole statement is false. What about the next line, where A is true and B is false?
Whole statement's true.
The whole statement's true? let's see if we can figure this out. First, we want to maybe do the A or B. True or false is true. And then over here I have B is false, so not B is true. I have a conditional statement that says if a true thing, then a true thing. That's true. Yep. What about the next line? Can you do the next line? We think false? False or true is true. Not true is false. If true, then false is false. That's the only time that if then. Are you seeing what I meant before where I was saying, like, if you don't have these rules in your pocket, this is going to be really, really hard. You're going to be like constantly looking shit up on your worksheet. But yeah, this one should be false. Last but not least, false or false? False or false is false. False. Yeah, that's the only time that an or statement is false, is when both disjuncts are false. If false, then this is going to be true. I don't even actually have to know what this is. If false, then whatever is always going to be. Yeah, if the antecedent is false, then the whole conditional statement is always going to be true. So the way that I look at this is I'm saying, okay, so these are the truth values for the whole statement in each of these lines, each of those lines representing a possible world with a different sort of truth value for A and B, A or B. And I'll identify here that, ooh, look at this. It's not always true. It's true when A is true and B is false, and it's true when A is false and B is false. Another way of saying this is it's true whenever B is false. That's what's going to make this statement true. If B is false, then this whole big complicated statement is going to be true. So again, Allison, you were wondering, like, what sort of goals are this? One of our goals is to be able to handle validity of arguments, but that's a little further down the road. What we can talk about this time is we can say that, like, well, this statement is going to be true whenever B is false, so if I want to know whether the whole statement is true or false, I can just go straight for B. I can just figure out, like, is B in fact true or false? And if B turns out to be false, then I'll know that the whole statement is true. If B turns out to be true, then I'll know that the whole statement is false. Does that make sense? Okay. Should we do another one? Shall we do another one that's a little more complicated? Good, because that's what the next slide is. All right. Yeah, this one's bigger, right? Yeah, like why? Yeah, why is it bigger?
There's more options.
Yeah, I have more simple component propositions in this. It's not just A and B now. Now it's A, B, and C. And I have a complex proposition here that says not if A then B and C is how I would read that out loud in English. It's not the case that if A then B and C. No, that's not how I want to say it. Yeah, it's not the case that if A then B, pause, and C is what I mean to be saying. Yes, Alman. That don't treat the negation as just a negative sign. So yeah, the temptation might be immediately here to try to distribute your negation and say, like, I've done some math before. I can simplify this and say not A then not B. Nope, that's not how that works.
That's not what you did.
Yeah, what I'm saying is it's not the case that if A then B. So that's actually the way that I would figure this out is I'd figure out, like, if A then B, and then whatever truth values I get for that, I'll just negate them. Yes, Kristen.
What's not the case that these
It's not the case that if A then B. So, for example, if A then B, well, here's an example of if A then B. If it's raining, then I'll bring my umbrella. I can say that, right? If it's raining, then I'll bring my umbrella. I can also say it's not the case that if it's raining, then I'll bring my umbrella. I can just keep stacking these things. In fact, if I wanted to get really, really weird, I could say it's not the case that it's not the case that if it's raining, then I'll bring my umbrella. I can do as many of those nots as I want. It's not the case that it's not the case that it's not the case that if it rains, then I'll bring my umbrella. And each of those times, I'm just negating whatever I said, whatever I'm saying after it.
I guess it's kind of like, I'm kind of having a hard time with it because we've been working with arguments. Now they just
Now we're just looking at statements. Yeah. But do we understand, like, you gotta handle statements before you handle arguments, because arguments are like multiple statements. Yeah. Yeah. So yeah, I get how that might be a little bit confusing. But so like, if I can say if A then B, then you can think of the negation as just saying it's false that if A then B, maybe? Or it's not really it's false that if A and B, because I'm not saying that it's false. I'm saying whatever the truth value of if A then B is, reverse that. That's all I mean by it's not the case that if A then B. And I have more than that. It's not just it's not the case that if A then B, it's not the case that if A then B and C. And this is a way more complicated truth table, or it's a bigger truth table at least. I don't know that it's actually more complicated. It's bigger, certainly, because I have 3 component propositions to look at. Yeah?
To make it easier, would you say that each one where C is false is automatically like the whole thing, the value of false because it's a convention?
I do know, yeah. So there are ways of shortcutting this. In fact, I think in your book it gives you a way of kind of like trying to work backwards and noting that like, all right, whenever C is going to be false, that whole thing is going to be false. So I'll just, every time C is false, I'll just like note that like I don't even have to figure out the rest of that line because I know that on line 2, it's going to be false. On line 4, it's going to be false. 6, on all the even numbered lines, the whole statement's going to be false because whenever C is false, the whole thing falls apart, right? So that's one way of doing this. Another way of doing it, too, might be to note that if this side, if the other conjunct of the statement is false, then the whole thing is going to be false. And this inside, the if A then B part, is always going to be true whenever A is false. And if A then B is true, then it's not the case that if A then B is going to be false. So whenever A is false, the whole thing will fall apart as well. So whenever C is false, the whole thing won't work. Whenever A is false, the whole thing won't work. But we can get a little more, I would say that's a kind of advanced method. I actually wouldn't recommend it at first. I'd recommend kind of working it out slowly and methodically. Because you can lose track. Like you're doing too much in your head is like what it amounts to. Try to keep as much of it on the page as possible, and you'll reduce the number of possible mistakes that you might make. I frequently encounter students who have difficulties with figuring out how to do this part. How do I generate all of the possible combinations of truth values for A, B, and C? Hopefully you got the impression of like how that worked. Let's see, on the last one, that like when I had A and B, I had 4 lines. How many lines do I have on this one?
You have 8.
8. I have 8. It's always going to be some power of 2. For every additional simple proposition that I get, I'm going to double the number of lines that my truth table needs to have. And this makes sense, I promise. If I'm just dealing with P, how many truth values can P have? 2. It could be true or it could be false. If I'm dealing with P and I'm also dealing with Q, a second one, P could be true or false. And whenever P is true, Q could be true or false. Whenever P is false, Q could be true or false. So I just double the number of cases that I'm looking at now. Because however many cases I was looking at for the truth value of P, I need to double that to now think about Q, because Q could be true or false in all of the cases where P was true or false. And if I add a third term, everything that I said before about P and Q, I'm going to have a version of that where my third term is true, and I'm going to have another version of it where my third term is false. So I'll double my number of lines yet again. So if I have 1 term, 2 lines to my truth table. If I have 2 terms, 4 lines on my truth table. If I have 3 terms, 8 lines on my truth table. If I have 4 terms, 16 lines for my truth table. And the method that I usually use for this, and this seems to be a pretty standard method for making sure that you get all of the different combinations of truth values here, is to say, all right, 3 terms, this is going to be 8 lines. Half of those are going to be true A, half of them are going to be false A. So right off the bat, I know I'm going to have 8 lines, half true A, half false A. Let's just do 4 A's in a row that are true, and then 4 A's in a row that are false. If I did 4 in a row on my first column, my second column for B, I'll do it in 2s. 2 in a row, 2 in a row, 2 in a row, 2 in a row. And if I just did 2 by 2s in my second column, in my last third column, your last column should always be true, false, true, false, true, false. You should be alternating every one. So if you find that you don't end up with that, then like you're going to have, there's a sign something went wrong. But my approach to this, and it seems like it works, and I think a lot of folks, once you just get enough practice with this, it becomes second nature. Figure out how many lines the whole truth table should have, and it's just 2 to the n. It's 2 where n is the number of simple components that you have. And then say, all right, half of those are going to be true A, half of them are going to be false A, and then however many in a row you did, half of that for the next column, half of that for the next column. Your last column should always be alternating every one, true and false. Okay. First things first, plug in truth values for A, B, and C over here, which takes a little longer if you're working it out by hand, but I can do it real fast. Boom. Those are all the truth values for A, B, and C. Just whatever it said over here on this left column, I'm just plugging it in over there in the complex statement. What now? What do I want to figure out next? Can I do the and?
No, you gotta go.
I can't do the and yet because I don't know what one of the conjuncts for the and is. Can I do the not? No, I can't do the not yet because I don't know what I'm notting. I don't know what is inside those parentheses. So let's do what's inside the parentheses first. That's always a good idea. If A, then B. A is true, B is true. If A, then B is true. Now, if A, then B is true, not. Or it's not the case that if A, then B is going to be false. Good with that one, Kristen? That was the, so yeah, whatever I just did. No, I'm just doing the first row, and then we'll kind of go down. Yeah. So if A, then B is true, when both A and B are true, that means it's not the case that if A, then B is going to be false. So I have a false thing and a true thing. That means the conjunction is false. So on that first line where everything's true, the whole statement's false. Yes, Kenneth.
Would you not apply the rules for the line?
The tilde.
The tilde to the A and B first if they're in parentheses?
That's that move that I was talking about. Like some folks want to think about that tilde like it's a negative sign in a mathematical operation and just distribute it across. It's not a negative sign. This is similar to mathematics in that it's a formal language, but it is not mathematics. Like we're not dealing with numbers and mathematical operators here. We're dealing with propositions and logical operators. So the negation is not quite the same as a negative sign. It doesn't distribute across parentheses that way. Yes?
So what I'm hearing so far is we start with what's in the parentheses.
Yep.
There was
And then work your way out. Yeah.
what we did with the tilde. That is what's in the parentheses.
Yeah, because the tilde is operating on whatever is immediately to its right, and what's immediately to its right is this parenthetical phrase. Yeah. Yeah, C is, well, it's off on the other side of the and. And so I know that, like, in order to evaluate that and statement, I need to know the conjunct to the left of the ampersand and the conjunct to the right of the ampersand. The conjunct to the right of the ampersand is pretty easy. It's just C. The one to the left of the ampersand is this business, that it's not the case that if A, then B. Next line. A is true and B is true. If A, then B is true. That means it's not the case that if A, then B is going to be false, which means false and false is going to be false. Next line. If true, then false is false. So negate that. It's going to make it true. True and true is true. Good. If true, then false is false again. Negate that. It'll be true. True and false is false. Good. And just keep doing it for every line. And you will find that there is exactly one scenario. There is one set of conditions under which that statement is true. It is this set of conditions. When A is true, and C is true, and B is false, that statement is true. Every other case, that statement will be false. Yeah. Once I've filled out this truth table, what I've figured out is whether or not this whole statement is true for every possible combination of truth values for A, B, and C. So what I've done is I've exhaustively explored all the possibilities that this statement could be considered under, and I found that only in one of those sets of possibilities did the whole statement end up coming out true. And it was on this third line where A is true, B is false, and C is true, every other time, any other like possible truth values for A, B, and C will make that statement false. So if somebody told me this, if somebody said it's not the case that if A, B, and C, and I said like, God, is that true? I'm not sure. I know that it's only going to be true in these scenarios, so now I can start looking for, like, if I want to know if that whole statement is true, I need to find out if A is true, B is false, and C is true. I've kind of focused my question about the truth of that statement to this question about, is this the scenario that obtains? Yeah, Kristen.
So in this scenario here, the and sign is representative of the interaction of A and B with C under this condition.
Yeah, actually, the ampersand, everything that's under the ampersand is representing the relationship of, it's not the case that if A, then B, and C. Yeah, that's right. Yeah, so this convention that we're kind of like, we're putting truth values underneath an operator, that's for like, whatever's underneath this arrow is this whole statement, everything that's in the parentheses. Whatever's underneath the tilde here is this whole thing, the negation of that parenthetical phrase. Whatever's underneath the ampersand here is the conjunction of everything to the left of the ampersand and everything to the right of the ampersand. Cool, cool, cool? Cool, cool? Cool? Don't forget you got this 2 to the n rule, the number of simple propositions involved in my complex proposition. 2 to the that power is going to tell me how many lines that my truth table needs to have. And we'll see it goes up as high as 64. Boy, will he ask us to do one that complicated? No, that's crazy. But I don't know if anybody has figured this out yet. Maybe some of you have a little bit of background knowledge on this kind of thing. This is maybe about the limit of what it makes sense for a human to try to like apply this method to. If it gets a lot bigger than this, then it starts to get a little bit silly. But I'll tell you what could like do this really, really fast, and it doesn't matter how complicated it is. A computer could. Yep. So this is like a form of doing logic that like computers can do very, very well. It's very, very close to computer programming. It's also very, very close if you consider those logical operators. They can be represented as circuit gates. So this is like you can build circuits that will like tell you the truth values of these statements. That's about as close as we're going to get to computer programming in this class, is this style of logic that plays very, very nicely with that application. Yes? Yes, this could be used for any argument. Yeah.
And like if you use like say like maybe this kind of the argument, it was me, and I said this place, right, and all this down, trying to make this whole table. You do that, that's like really any argument.
Yeah, you could do any argument this way. If you can represent it in propositional logic, and the idea behind propositional logic is you can do any statement in propositional logic. We don't have all the tools yet. There are some kinds of statements that you'd have to take Philosophy 310, our formal logic class, that is like all propositional logic and nothing else. There are other tools that you can have. So we don't actually have the tools to say everything that you can say in propositional logic, but we have a lot of them already. Yep. Yes?
I thought it was all induction.
That's true. I'm sorry. Yeah, good point. Excellent point. Yeah, I won't be able to determine whether or not inductive arguments are strong or weak with this. I'm only going to be able to tell whether or not they're valid. And I haven't even gotten to arguments yet. We're still just looking at individual statements. Because, you know, we walk before we run.
Oh.
Yes?
Okay, so like in theory, you'd have a proposition, what's that word?
Proposition?
Yes, a proposition statement, like multiple of those plus conclusion, and then you do all of this for that, and that.
So
would be
yeah,
argument.
the way that we would do this for a whole argument is we do a truth table that has premise 1, premise 2, and my conclusion, or however many premises I have. Premise 1, premise 2, premise 3, and my conclusion. And I'll do truth tables for all of those statements. And I'm going to be looking for, like, is there a scenario where all the premises are true, but the conclusion's false? If I can find that, then I'll know, like, it's invalid. And this is the sort of thing that works as long as this stays simple, or it works. A human can do it on paper as long as it stays simple. When it gets really, really complicated, this method starts to lose its utility for a human working it out on paper, but it never gets too complicated for a computer to do. That's maybe not true. It sometimes gets too complicated for a computer to do, but like computers aren't as susceptible to this, like, oh, it's taking a long time, as humans are. They can do their operations really, really fast. Okay, you got a worksheet, which, how much time do we have? Ooh, not a lot of time. So we're not going to be able to do all of this worksheet, but we should do some of it together, because this ain't easy. Wesley, you mind if I put this here? All right. Let's start with number 1 on our worksheet. Everybody got it? I did it again, didn't I? What a jerk. Maybe. I'm starting to lose it. Rosenfeld, senile at 37. What a sad story. You can start 1, 2, 3, 4. Make sure that Regina gets one of those. 1, 2. You can start passing those around for me. Thanks. So the first one on this worksheet, if you haven't gotten it yet, that's okay, I'll write it out. The first one on this worksheet is P or not P. And I want to know, I want you to make a truth table for me on this and tell me under what conditions is this statement true. How many lines is this truth table going to have? I see somebody saying 4. I heard somebody saying 2. Which is it? Is it going to be true? How many simple component propositions are in this? 2, I hear? I heard somebody say 1. I heard somebody say 2. What are the 2? Yeah. True and false. No, true and false are not simple propositions. My simple propositions are the letters in this. There are 2 P's, but that's just P twice, right? I don't have P and Q, right? If P is true here, it's going to be true here. If it's false here, it's going to be false here. So I only have to worry about this when, like, P is the only variable in all of this. It could be true or it could be false, and that's it. When P is true, it's true over here and it's true over here. When P is false, it's false here and it's false when it occurs later in the statement. Good so far? My next question is, do I try to do the negation of P first, or do I try to do this disjunction? I heard people whispering negation. Can I do the conjunction before I've done the negation? No, because the conjunction is saying P or not P, right? So I have to figure out what not P is. It's not complicated. It's just the opposite of whatever P was. If P is true, then not P is false. If P is false, then not P is true. So I have P or not P, where P is true and not P is false. True or false? What's the rule for or? At least one has to be true. So true or false is true. False or true is true. Boom. This statement is true when P is true. It's also true when P is false. Another more elegant way of explaining that would be to say, this statement is always true. First, because I am not able to figure out what the disjunction is until I've figured out what the tilde is. Because it's P or not P, right? Sure. This is what's known as a tautology, by the way. Tautologies are statements that are always true. Sometimes people float tautologies and they try to sound very wise. They'll say things like, it is what it is, or boys will be boys. Like, yeah, it's always true. Another way of looking at a tautology is that it's kind of empty. It doesn't really tell you anything. And this should make sense. P or not P, right? Either it's the case that P or it's the case that not P. It's got to be one or the other, right? There's no way that it could be neither one of those. So yeah, this is always going to be true. Cool, cool?
This is always going to be true whenever P happens or something?
Yeah, we could get into like existential import sort of stuff, I suppose, but like let's not mess with it. P could be true or it could be false. Those are the only two options for P. Either P is true or it's false, and apparently it doesn't matter if P is true or P is false, because P or not P is going to be true no matter which case I look at.
So what's on the other side of that line, the right side, that's what happens when P is true or P is false.
Yeah, so this line tells me what happens when P is true. This line tells me what happens when P is false. And apparently, P is true makes the statement true. P is false makes the statement true. And those are the only scenarios that like we could possibly consider. P's got to be either true or not true. P or not P. Yep. Let's look at number 3. Jump ahead. Oh, yes, Allison.
Are we able to change the table?
How would you like to change the table?
I really just like having to go backwards to find out where and place the, instead of going just straight forward and creating like little columns for what you just found out.
Mm-hmm.
You have to go backwards and put the truth values underneath, like, or,
So let's try this again then, and you tell me how you would approach it. Is this good so far, the way that I've laid it out? True, false, true, true, false, false. What would you do next?
I would rewrite it like to the side of that, and I would say true or false. For the first row.
For the first row?
Yeah.
What do you mean you would rewrite it?
Like I would create another column.
Oh, like this?
Yes.
What would you write in that column?
True with a wedge, or and false.
Because this is negated, so it's actually false.
Yes.
And then you would figure out what this is. Yeah, you just do another column. I suppose you could do that method. It's gonna get messy when this gets more complicated. So actually, I'd recommend not. This is like playing music. Like, play Twinkle Twinkle exactly like it's on the page before you start doing some jazzy stuff, right? So yeah, if you can do this, then you can start doing some abbreviated methods. In fact, I think your book suggests an abbreviated method for this, similar to what Omar was talking about, where you do kind of work backwards, starting with like, what's going to make this whole thing true, or what's going to make this whole thing false, and then working backwards from there. But I wouldn't recommend it for starting out. Let's look at number 3 with what time we've got left. This one's a little more complicated. P or Q if P or Q, then P. How many different independent statements do I have here? 2, right? I have P and I have Q. So how many lines is my truth table going to have? It's going to have 4. True, true, false, false, true, false, true, false, true, 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 everything's true. In this one, Q is false. In this one, P is false. And in this one, everything's false. Do I have to do what's inside the parentheses first? Yeah, because that's going to give me my antecedent, and only then will I know whether the if-then statement is going to be true. So P or Q, when they're both true, it's true. When only one of them's true, 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 or, right? Or says at least one of them has to be true. In this one, at least one of them is true. In this one, neither one of them is true. Now it's false. So now I have an if-then statement where this is the if part and this is the then part. Goodness. If true, then true. True. If true, then true. Still true. If true, then false. That's the one. That's the one that makes the conditional statement false. If false, then false. I don't even have to know the then part. If false, it's going to be true. So this is the whole statement. It is true on line 1, it's true on line 2, it's false on line 3, and true on line 4. If I was going to explain what its truth conditions are, I could just say, it's true here, it's true here, it's true here, it's true here. If I wanted to be a little more elegant about it, I could say, it's true unless P is false and Q is true. That would be like a much quicker way of saying it. And you might notice on your worksheet that, like, flip it over to the back, you look at number 9 or something like that. This can get arbitrarily more complicated.
So we got brackets.
So notice what's going on 9. I have P, Q, and S. How many lines is that truth table going to have? That's going to be an 8-liner. Yep. Yep, 2 to the 3rd. We'll have a homework assignment on this. Tell you what I'll do. I'll post the homework assignment on this, but I'll make it due Friday midnight.
So we can have class.
And then we'll have class on Friday. And if hopefully you've done at least one attempt on it by then. Save yourself at least one attempt till after class on Friday. And what we'll do on Friday is we'll workshop more of this stuff. Because we've got to have this down before we start doing much bigger truth tables with like multiple premises and a conclusion. Sound good? All right. I will see you on Friday.